everyone, I'm Selena. Today I'm going to demonstrate my DURF final presentation, and my topic is design of patient scheduling systems. In motivation, the number of Americans ages 65 and older will more than double over the next 20 years, reaching 18 million in 2040. The number of adults ages 85 and older, the group most often needing help with basic personal care, will nearly quadruple between 2000 and 2040. It is obvious that shortage of available hospital beds make it difficult for patients to be admitted to the hospital, so that triage policy plays a major role in the medical system. In this project, an optimal scheduling policy is going to be implemented to make decisions when patients enter the queue. The policy will select specific patients to use the resource, which has limited quota. In the part of problem formulation, there are two approaches in this project. In approach 1, the evolution law of the stage of the care unit best defined as the occupied beds in the care unit at time t plus the total number of new admitted patients in the care unit at time t, and minus the number of patients leave the care unit at time t. The evolution law of the queue length of each patient type defined as the queue length of patient type at time t plus the new arrival patients at time t minus the admitted patients at time t. And the state of the system at time t is composed of the occupied beds in the care unit at time t and the queue length of each patient type at time t. The reward of the system at time t defined as the total queue length of each patient type. And the optimization problem here is to minimize the rewards. In approach 2, each patient type will assign a target waiting time. And the state of the system at time t is composed of the number of I-type patients in the queue and the number of the patient arrival today to the number of patients that have been in the queue more than 2 times the target waiting time plus 1 day. The penalty of the system will be 0 penalty if the patient waits less than or equal to the target waiting time. But if it waits larger than the target waiting time plus 1 day, then the penalty will be 1. And if the patient waits larger than the target waiting time by target waiting time plus 1 day, then the penalty will be the square of the target waiting time plus 1 day. And it is a summation of the penalty of one of the patient type. And the optimization problem here is to minimize the unfairness of scheduling. In optimization problem, the first approach aims to minimize the total waiting time using Bellman equation. Q target indicate the Q function under state S, taking action A, which is composed of the reward at time t, and the minimum Q function at next state ST plus 1, taking action AT plus 1. The second approach aims to reduce the unfairness of scheduling, as other scheduling schemes may prioritize the patient with shorter service time. This could lead to suffocation, since the low priority patient may never be scheduled. The algorithms in this project are the traditional crane scheme, first in, first out, priority based, and shorter job first. And the reinforcement learning algorithm, DQN, FAIR, and PPO. The algorithm in this project will be structured under this reinforcement learning structure. In reinforcement learning, the structure is implemented in cyclic mode. Firstly, the agent, which is the scheduler, interact with the environment by observing its state and taking action accordingly. Then the environment gives back a reward according to the action and move to the next state. The reward here will be the total queue length. The major objective of the agent is to minimize its total reward within a final period. Then I will first cover the deep queue network. DQN execute the selected action from current state using epsilon greedy algorithm and saw the agent experience in the form of tuples in the replay memory. The tuple consists of the current state, the action taken from the state, the reward at time t after performing the action, and the next day information. And the tuple will store into the training data. Later, in each training in the main network, samples are randomly selected from the replay memory and input to the main network and the target network. The main network computes the predicted Q value based on the current state. The target network has the same structure as the main network. Every time, the next state information from the tuple will be passed as the input and returns the best target Q value among all possible actions. And later, the loss will be computed by the difference between the predicted Q value and the target Q value from the target network. The main network will be trained in every time step, but the target network will not be trained in every time step. The target network is the clone of the main network, such that the weights in the target network are copied every certain amount of time step from the main network. Let me move to proximal policy optimization. PPO is implemented using actor-critic model, which use two neural networks, which are the actor network and the critic network. The agent updates the networks by using all the batches in the memory, after the memory has accumulated a certain number of experience. And upon completing the training, the agent hears all the experience from the memory and continues to interact with the environment again. The actor model is applied to learn the action to be taken under current state and receive states as input and output the probability of each action. Using a probability distribution, the agent can select an action by sampling from the distribution. And the critic model updates the parameter by TD error. The model receives the states as input and estimates the value function of that state. The output from the actor model is a probability ratio defined as the new policy over the old policy. The output from the critic model is a generalized advantage function, which defines the performance in a state by taking a particular action and compute the TD error to update the model parameter. And the generalized advantage function and the probability ratio will pass to the clip function to constrain the size of updates, which it does by making PPO greedy in favoring actions with positive advantage and rejecting actions with negative advantages. This project aims to conduct a simulation using real-world hospital data. The patient admission data is from BIDMC, which located in the United States, includes 42 care units and 9 patient types. Simulation results show that DQN provides the shortest total waiting time and average waiting time in different capacity. DQN may not provide the best result in the beginning, but after training some batches in the network, the waiting time converges to a level that the increase of the waiting time becomes stable. In the result, DQN gives the shortest total waiting time, and the PPO performs worse than the DQN. The performance of fair scheduling also provides good result. And the number inside the bracket is the target waiting time of each patient type. Under fair scheduling, the average waiting time is much more balanced than under the other algorithm or scheduling method. The urgent patient type must wait a long time under shortage of first, which is not infeasible in the hospital situation, as the urgent patient type should be in the first priority in using the resource. In this project, I have successfully developed the model of simulating real-time hospital scheduling in BIDMC, and the algorithm in reinforcement learning outperforms compared with the traditional scheduling system to reduce the total waiting time. The project showed that there is potential in scheduling systems that employ reinforcement learning. Under reinforcement learning, the project mainly tried 2 different algorithms, and DQN gives better results than PPO. And it is the end of my presentation.